Welcome to my 13th lecture of Control System 2. So last two lectures we have discussed about the review of linear algebra. So today we are going to start to understand the solution of linear time invariant state equations. So these are the topics we are going to cover with the coming lectures. The introduction, then we are going to understand the solution of state equation using Laplace transform approach, solution of state space equation using time domain approach, then solution of then the solution of homogeneous state equation. Then we will understand that the computation of e to the power at or the state transition matrix, then properties of state transition matrix, and at the last we will see that how to solve the non-homogeneous state equations. So with these objectives or contents, we are going to start that solution of linear time invariant state equations. So now the very first thing is coming in our mind, that why we want to solve the states equation, because already we have seen in the previous lectures that a dynamical system can be represented using time domain, using the state equations and the output equations. And now we want to know that why we want to solve the state equations. Mainly we want to solve the state equations for two objectives: to compute the time response, because you can see that a LTI system can be represented using x dot t equal to a into xt plus b into ut, and here we are obviously assuming that there are n number of states are there, and the output equation yt equal to c into xt, and the initial conditions are given. Now if this is the representation of any LTI system, it can be MIMO or it can be CISO, it doesn't matter, but we want to compute the time response. So now if you see the time response or the output of the system, you are observing that it is yt equal to c into xt. So if you want to know that for a given input, so suppose if for a given input, suppose ut is given, and if we want to know that what should be the output response of the system yt, then you are observing that we need to compute x of t. So how we will compute the x of t? Now if you see the first equation, which is a set of first order differential equation, that is x dot t equal to a into xt plus b into ut. So we need to solve this set of first order differential equation to know what is the xt. So if we want to compute the time response of a system, then obviously we need to solve this state equation. So this is one objective, and another objective is to determine the internal stability of the system, because we understood from our previous experience that the transfer function only reveals the input output relation or input output stability also, which is known as Bibo stability. Maybe a system is Bibo stable, means for a bounded input you are observing that output is bounded, but it may not guarantee that the system is internally stable, means it may happen that other states are going to diverge. So that's why if we want to examine the internal stability of the system, we have to see that are all the states are close enough to the equilibrium point, or they are converging to the equilibrium point when the time goes to infinity. So we have to see, or we have to guarantee that if a system is internally stable, then all the states of the systems are going to converge towards the equilibrium point. Though formally we have not introduced the means the definition of the equilibrium point, but you can understand in this point that the equilibrium point are those points for a system. If the system will start from that point, it will ever it is not going to leave that point. It will be it will be in that point only. Means what we want to mean that if a system is going to start at the equilibrium point, then there will be no dynamicity. It will be forever will stay at that equilibrium point. And so to compute the equilibrium point for a unforced system, we will make dx by dt is equal to 0. so there will be no dynamicity in the states. So that this point I will discuss definitely, but at this moment it is very important to understand that once we will solve this set of differential equation, then only we will come to know about the x of t. Once we will know the x of t, then only we can see that whether the x of t means all the states of the systems are going to converge to the equilibrium point as time goes to infinity, or we can see whether they are close enough around the equilibrium points or not. So with these two objectives, we want to solve this set of differential equations, and here in this discussion we will understand that how we can solve this set of differential equation effectively. So the techniques we will use, that is using Laplace transform, completely the solution can be achieved using Laplace transform approach in frequency domain, or we can go for the time domain approach. But most interesting thing and most important thing is the time domain approach, because as the system representation is in time domain, so we want to know that how the time domain approach, with the time domain approach we can get the solution. So now you can, if you see that the equation is x dot equal to a into xt plus b into ut, and if we want to use the Laplace transform approach, then we have to take the Laplace transform of the state equation. So if you take the Laplace transform of the state equation, then you can write s into x of s minus the initial condition x of 0, then a into x of s, and then plus b into u of s. So here the u of s is the Laplace transform of the input, and x of s is representing the Laplace transform of the states. Now if you rearrange this equation, then we can write the x's as it is indicated in equation 1, that x of s is equal to s minus I into a inverse into the initial condition, that is x of 0, then plus si minus a inverse b into us. Now you can see the advantage of Laplace transform. So it was a set of first order differential equation, and once you will apply the Laplace transform, then in frequency domain it become algebraic equation. So now if you want to compute the time response of the system, then you know that the output equation is simply, that is y of s. If you take the Laplace transform of the output equation, that is y of s is equal to c into x of s. And now if you substitute the expression of x of s into the expression of y of s, then you will arrive to the equation number 2, and where you can see the two parts of the response very clearly. So y0 of s representing the zero input response, and yu of s is representing the zero state response. So now if you see the or examine the equation number 2 carefully, you can observe that once the system will be given, then you will come to know the a b c matrices. So a b C matrices are known, and also initial condition will be given. So x0 also will be given to you, and the output has to be calculated for the given input. So us also will be provided, means ut may be provided, that for what input you want to compute the system response. Now from this expression it is very much clear that one important thing you have to compute, that is si minus a inverse. So this is the very important thing you are observing, that we have to compute si minus a inverse. But now we will apply here the Laplace transform approach. So that's why you can see that how we are going to compute the response of a system purely using Laplace transform approach. So we will understand with an example. So suppose a given system is represented, which is a third order system. So it is the dimension of A matrix is 3 by 3, and the dimension of B matrix 3 number of rows, 1 column is there, and here the ut. So this is the e to the power minus t is representing the system input. So it is exponential input has been given, and y is given 110x, and the initial condition x0 is given 1 0 2 transport. Basically x0 is given 1 0 and 2. So now what you have to do here thing is that we have to solve the preceding state equation and obtain the output for the given exponential input and find the eigenvalues and the system pole. So we will concentrate the first part first, that solve the preceding equation means if we solve the x dot equal to ax plus bu, then only we can compute the y, because y equal to simply c into x. So if we know the x, then we can compute the output y for a given input. Here particularly the input is given the exponential input. So according to our discussion that we have to compute first the Si minus A inverse to compute the xs, because x0, b and us is given. So now we to compute the Si minus A inverse in frequency domain. So we have computed the Si minus A, and then we have computed the Si minus A inverse by computing the adjacent of Si minus A and determinant of Si minus A. So this is the expression you can see for the Si minus A inverse. Now we want to compute the xs using the formula what we have stated, and to know that xs we have to know the u of s. So u of t is given e to the power minus t. So u of t here it is e to the power minus t. So u of s we can compute very easily, that is 1 by s plus 1. So now here you can see that x of s will be in dimension of 3 cross 1. Why? Because you see Si minus A inverse, definitely it will be n cross n, and x of 0, that is also here particularly for the particular system we should write. So here thing is that so this is 3 cross 3 and this is 3 cross 1. So from here you can see that we will get 3 by 1 ultimately, and here also this is 3 by 3, and b is also 3 cross 1, and us is 1 by 1. So ultimately you will get from here 3 by 1. So basically x of s having 3 component, that is x1, x2 and x3. So that's why so don't be confused with this, it is x1, x2 and x3. So that's why if you substitute the Si minus A inverse and the x0 what it is given and b and us what it is computed, then you will get the 3 states expression in frequency domain, x1s, x2s and x3s. Now if you see the expression of y of s, it is 1 1 0 x1 of s, x2 of s, x3 of s. It means that y of s is equal to x1 of s plus x2 of s. So already we have the expression of x1 of s and x2 of s. We will substitute and we will get the ultimate expression of y of s in time domain, and which can be written in fraction partial fraction expansion, such that we can compute the y of t, that is in time domain. And here we can observe that the input pole, that is s plus 1, will be cancelled out with the zeros of the system. So that's why we will get the partial fraction expansion in this form, and ultimately the yt we can see that it is 6.5 e to the power minus 2t, 19 e to the power minus 3t, minus 11.5 e to the power minus 4t. And most importantly here you can see that the exponential terms are the poles of the system, that is you see minus 2, minus 3 and minus 4, because immediately if you calculate the determinant of Si minus A equal to 0, then you will find that the poles of the system and the eigenvalues of the systems are same, that is minus 2, minus 3, minus 4. So whether the output is going to be converged or as well as the states are going to be converged, it depends on the pole location. You see here fortunately all the poles having the poles of the systems are located, or eigenvalues having negative real part, and the poles of the systems are located at the left hand side of the S plane, and that's why you are finding that the output is also going to be bounded, means it is going to be converged as t. So output you can say that here from this expression, as the limit t tends to infinity, as the time is very large, yt is going to be vanished, that is 0. Fine. And here, by observing the expression of yt, you can comment about the Bibo stability, because you see we have given a bounded input e to the power minus t, okay, which is a bounded input. For that you are finding that the output is also bounded, so at least here we can guarantee the system is Bibo stable. But when we are analyzing the system using state space representation, we can also comment about the internal stability of the system. That will be the next topic of our discussion, but which is very much connected about the solution of the state equations. So we have to correlate the things whenever the theories are going to appear. Fine. So now one important thing, so this is the way we can calculate the system response in using using the Laplace transform approach. But thing is that one thing you can observe in the output equation, that if we want to calculate the y of t in time domain, okay, then we have to take the Laplace inverse Laplace at the both the side. And if you take the Laplace inverse at both the side, c is constant, x0 is also constant, okay. So now you're observing that actually you have to take the Laplace inverse of si minus a whenever you are going to compute the y of t, along with, because you see you can because c is constant, x0 minus is constant, b is constant, okay. So this you can take it out, and also you have to take the Laplace inverse of this term. But most important thing is that we have to take the Laplace inverse of si minus a inverse if we want to compute the frequent time response of the system here. So now we will give a special focus on si minus a inverse. This term will play a key role when we want to determine the or when we want to solve the state equation in or using time domain. So that's why our next discussion will be that about that Laplace inverse of si minus a inverse, or we will start with si minus a inverse. So let us further investigate the quantity si minus a inverse in the expression of y of s. So you can remember the geometric series, that is 1 minus alpha to the power minus 1 can be written, which is a infinite series, that is 1 plus alpha square plus alpha cube plus the terms will come. Fine. Now you can so same thing, that geometric series can be written for a matrix A, which is a square matrix, that is n by n. How? Now you see that is si minus a inverse, that can be written, if you take the s common here, so that can be written 1 by s I minus a by s inverse. So now it is very much similar with the expression 1 minus alpha minus 1. So accordingly, if we write 1 by s is 1 by s into I plus a by s plus s square by s square, like that the terms will be there. Now if we multiply 1 by s, then ultimately we are getting 1 by s into I plus 1 by s square into a plus 1 by s cube a square. Now our interest is to take the Laplace inverse of this term. Okay, we want to see how the Laplace inverse of si minus a inverse will be. So now to get the Laplace inverse of si minus a inverse, if you want to take the Laplace inverse, then basically we have to take the Laplace inverse. So it will be all Laplace inverse. Here some symbol mistakes are there, so it will all Laplace inverse. So we have to take the Laplace inverse of individual terms, this term and this term, and to get the Laplace inverse of these terms, we will take the help of the formula, that is Laplace inverse of 1 by s to the power n plus 1 is equal to t to the power it will be t to the power n by n factorial. Fine. So now with this we are finding that the Laplace inverse of si minus a inverse will be also an infinite series, but in time domain now we have written I plus at plus a square t square by 2 factorial, a cube by t cube by 3 factorial, like that the terms will be there. Okay, so can you remember, can I write in the compact form, or can I define this series in such a way that we can write the Laplace inverse of Si minus A inverse in a compact form? So now for that recall the series expansion of e to the power alpha, where the alpha is a scalar quantity. So e to the power alpha is equal to, we can write 1 plus alpha square by 2 factorial alpha cube by 3 factorial. So now if you just compare with this e to the power alpha and the expression what we got here, so basically alpha is equal to AT. Fine. So now that's why it has been defined. So now this similarity is there, that's why we are defining. So that is a very important thing you have to understand. We are defining the Laplace inverse, okay, Laplace inverse of Si minus A inverse, Laplace inverse of Si minus A inverse as a e to the power A into t. Okay, so this looks so similar to the above formula that we define the matrix exponential. So that's why Laplace inverse of Si minus A inverse, we will define it as a e to the power At. Okay, which is basically I plus At square by 2 factorial At cube by 3 factorial, which in a summation form can be written r equal to 0 to infinity t to the power r a to the power r by r factorial. Okay, so later on, if we have, or we will find that there is a Laplace inverse of the term of Si minus A inverse somewhere we will find, then definitely we will, by the definition, we will write in the form of e to the power At, or sometimes it is written phi of t also. Okay, and we will define this e to the power At, that is matrix exponential, little bit later. Okay, means the term is there, a specific term is there to describe the e to the power At. Fine. So that's why from the formula, above formula, for a n by n matrix A, e to the power At is also will be a n by n matrix, but we are not computed the e to the power At. So this is a claim only. Later on we will see that if we are computing the Si minus A inverse and Laplace inverse of that which is indicated by e to the power At, that e to the power At also will be a n by n matrix, and we are interested basically to know what will be the elements of a e to the power At, and because this that matrix exponential is going to play a very vital role to compute the time response and as well as to determine the stability of a system. So now we want to examine what is the use of this Laplace inverse of Si minus A inverse, which is defined as a matrix exponential, that is e to the power At. So that's why we will try to compute first the impulse response of the system. Let us see what will be the impulse response if the system is represented in state space. Okay, so we know that we will start from in a little bit different way, because we know that if a system representation is given, suppose a system is given x dot equal to ax plus bu, okay, and then we can write that, and also y equal to cx, then the transfer function gs will be equal to c into Si minus A inverse into b. Fine. Now what is gs? Gs is equal to basically the ratio of Laplace transform of output to the input, Laplace transform of input, when we are assume that all initial conditions are 0, and we know that the Laplace transform of impulse input is equal to 1. So that's why u of s basically is equal to 1. So from this expression we can see that y of s is equal to g of s into u of s, and for the impulse response u of s is equal to 1. So if the u of s is equal to 1, then we are getting basically y of s equal to g of s. So g of s, from the formula we know that is c into Si minus A inverse into b, and if we compute the Laplace inverse, then we will get the impulse response in time domain, that is y of t Laplace Laplace inverse of y of s, and the expression of y of s, we are finding that it will be ultimately c into Laplace inverse of si minus a inverse into b, and Laplace inverse of si minus a inverse of b, just now we have defined it is e to the power at into b, e to the power at. So ultimately the y of t, we are finding that it is c into e to the power at into b. So if a system representation is given, that is in state space, that is x dot equal to ax plus bu, and it has been asked to compute the impulse response of the system, and obviously y equal to cx, then impulse response of the system, if we want to compute, then we can use this expression directly, that is c into e to the power at into b. So we are calculating the time response, means the impulse response, directly in the time domain. But to compute the impulse response in time domain, we have to compute e to the power at. So till now we don't know how to compute the e to the power at. We have defined, so e to the power, you don't think that this expression will help you to compute the e to the power at, because it is not in a compact form, it is an infinite series. So we have to know that how to compute, what are the method exist to compute the e to the power at. Just to make you understandable that if we want to compute the impulse response in time domain, then we are finding that we have to compute the e to the power at. Okay, sometimes the impulse response is denoted by ht, so the impulse response ht also is equal to c into e to the power at into b. Fine. Now, so at this moment we are interested to know how to compute the e to the power at. So that's why next question has been asked, how to calculate e to the power at analytically. There are several approaches are there to compute e to the power at, but in this course I'm going to discuss few of them, and they are the Laplace transform approach, diagonalization, and Cayley-Hamilton theorem. So in this flow of lecture only I'm going to discuss about the Laplace transform approach and using Cayley-Hamilton theorem, and the computation of e to the power at using diagonalization approach we will discuss when we will discuss a topic called similarity transformation. Okay. So, and also we are interested, at the same time we are interested to know that here we have computed the time response, means impulse response of the system. This is the expression of the impulse response of the system. But in general, if we want to solve the state equations in time domain, what would be the way? So that's why in general, means for any input, if you want to compute the system response, or if we want to solve the system, that means state equations, then we want to know in general how the state equation can be solved. So we will give these two answers simultaneously, that how to compute the general, how to solve the general state equations, and also along with that we will discuss how to calculate e to the power at analytically, because you will find that to compute the general to solve the general state equation we require the help of it, or require to compute e to the power at, that we will realize just now. So now that's why we will again recall what was our problem statement. Problem statement was what? Now a linear time invariant system is given to you, that is x dot equal to ax plus b into ut, and yt equal to c into xt, and the initial conditions are given, and you have to solve xt. That is the objective. Now we will discuss the solution of xt for the two cases. First is for homogeneous case. For the homogeneous case we will assume that u is equal to 0, and for the non-homogeneous case where we will not assume that u is equal to 0. So first case, if we consider then the homogeneous system is represented by this, that x dot equal to a into xt and yt equal to c into xt. Here there is no input to the system. So now the question is that if there is no input to the system, then how the system will be, who is going to drive the system? The system will be driven by the initial condition. Okay, so that's why if the initial conditions are exist, then how without input the system is or system states are going to evolve, and subsequently the output of the system is going to evolve. That we are going to study when we can solve the system equation, that is x dot equal to a into xt. So let us start with that, and now here important thing is that xt is belongs to Rn, means there are n number of components are there. Now to understand the solution of a homogeneous system, we will start with the scalar system, okay, which will help us to solve for a vector case. So scalar case means first we will assume that only single differential equation is given, means x dot is equal to a into xt, where xt belongs to R. So a is also belongs to R. Fine. Now if we want to solve a single differential equation, something like x dot equal to a into xt, how we will do? So suppose I am applying the Laplace transform approach. So we will take the Laplace transform of this equation, a is into xs minus x of 0, a into xs, and ultimately the x of s can be written x of 0 by s minus a. Now if we want to take the Laplace inverse to write what is x of t, then what will be the Laplace inverse of 1 by s minus a? So you will find that the x of t, which is computed in the next slide, that is e to the power at into x0. So this is a very simple and straightforward solution. So if we have a single scalar differential equation, then x of t we are getting e to the power at into x0. Now we will extend this idea for a nth order system. So now we have a state equation with a dimension of n. So x dot equal to a into xt, and definitely if xt belong to a Rn, then definitely the dimension of a will be n cross n. So a is also belongs to Rn by n. So now similar way we will apply the Laplace transform, that is a into xs minus x of 0, a into xs. And then so here one mistake is there, it will be capital X of s, and x of s we can write by rearranging that si minus a inverse into x of 0. So now if we want to calculate the x of t from here, then we have to take the Laplace inverse at both sides, and we are finding that ultimately we have to calculate Laplace inverse of si minus a inverse into x0, and already we have defined that Laplace inverse of si minus a inverse will be e to the power at into x0. So it can be written e to the power at x naught is equal to phi of t x of 0. Okay, so now you can keep why we have defined that matrix exponential, because here you see that we are keeping the similarity, because similarity what, now for the scalar equation you see you got e into e to the power small a into x of 0. If we are getting a n by n matrix, for that it will be simply e to the power capital A into t x of 0, but we are more interested to know how to compute e to the power at, because here for a non-homogeneous case you are finding that to calculate x of t, that x of 0 will be given, but we have to compute e to the power at from the A matrix, and hint is that we have to compute Laplace inverse of si minus a inverse. But this is not the only way to compute e to the power at. By Laplace transform approach we can go for, as I told you, that Cayley-Hamilton theorem as well as the diagonalization approach. One by one definitely we will see. So now we will summarize here what we have discussed till now, that suppose we have a homogeneous state equation which is linear time invariant, that is x dot t equal to a into xt, and where xt belongs to Rn, so definitely a will be a n by n matrix, and the solution can be written, that is x of t is equal to e to the power at x naught, and if we want to calculate the output, that output we know that yt equal to, so here output equation I have missed, you can write output yt equal to c into xt. So once the xt is known, you can compute the output also. Yt will be c into e to the power at into x of 0. And now we will formally give a name to e to the power at, that is e to the power at also will be a n cross n matrix, that just now we will see that how it becoming a n by n matrix, which is called state transition matrix. Okay, why it is called state transition matrix? Because you see, if you know x0, the initial condition of the state, then you can compute x of t if you know the e to the power at. Any time t greater than equal to 0, if you want to compute what is x of t, then you can easily compute if you know e to the power at. So it is a state transition from initial condition. What is the transition here? From the initial condition, if you know, that you can know at any time t greater than equal to 0 what is xt if you have a knowledge of e to the power at. Okay, and my claim is that e to the power at is also will be a n by n matrix. Fine. So let us see with example what or how to compute e to the power at using Laplace transform approach. First approach will be Laplace transform, and we will discuss with example, which is very easy to understand. That suppose we have a LTI system which is homogeneous, so ut is equal to 0, so xt equal to a into xt, and here you can see that xt belongs to R of 2. Okay, and here 2 by 2 matrix, x0 is also given, and we have to find the state transition matrix phi t, and also we have to compute x of t. Okay, so what is the way to compute phi of t or e to the power at? Now the formula is that using Laplace transform approach, phi of t or e to the power at, we have to compute Laplace inverse of si minus a inverse. Okay, so first of all, let us see what is si minus a inverse. So that's why first si minus a is computed, then si minus a inverse is also computed. Okay, so si minus a is ultimately 1 by s square plus 5s plus 6, s plus 5 and 1 minus 6 and s. Now we want to take the Laplace transform or inverse Laplace transform of this expression. So Laplace inverse of si minus a inverse means we have to take the Laplace inverse of each term, because here you can see that 4 terms are there, that is s plus 5 by s square plus 5s plus 6, 1 by s square 5s plus 6, minus 6 by s square plus 5s plus 6, and s by s square plus 5s plus 6. Okay, so now individually we have to calculate the Laplace inverse, and for that we have to take the you have to compute the partial fraction expansion, and once you have the partial fraction expansion, then you can compute the e to the power at. Okay, in this way, this will be the expression of the e to the power at. So now you see e to the power at also a 2 by 2 matrix, and most interestingly, if you see each of the term, all are exponential, and the exponential terms having the power where all the poles of the systems are sitting. Where? Because you see the poles of the systems are for this system you can write that is s plus 2 into s plus 3, so the poles at minus 2 and minus 3, and you can see that in all the exponential terms that the poles are sitting. So this is the expression of e to the power at. And now if we want to calculate the x of t, that is phi of t into x of 0, and here in this problem already the x of 0 is given, x of 0 is 1 0, so if you multiply e to the power 80, so there will be no problem because it is 2 by 2, and here x of 0 is given 2 by 1, so ultimately x of t you will get 2 cross 1. Basically it is the expression of x1 of t, x1 of t, and this is x2 of t. So you will get all the state expression, how the state, now you can visualize how the states are going to evolve over the time. If you want to plot how the x1t with respect to time is going to vary, you can plot it. And from here it is very much clear that as limit t tends to infinity, that x1 of t is going to be 0. Okay, it is going to decay. Why it has happened? Because due to -2 and -3, just you imagine that if some of the poles are located at the right hand side, instead of getting minus term, you will get the plus term. So at that time you cannot able to guarantee that the states are going to be 0 as t tends to infinity. So this discussion having great impact when we will discuss the stability of the system, but just time being you remember or you observe these other things are associated with the e to the power at and the solution of xt. Similarly, for this case t tends to infinity, you can also guarantee that other state is also going to converge to 0. Okay, so this discussion definitely we will recall when we will discuss the stability of the system, because e to the power at means the elements of e to the power at. Here you see the elements of the e to the power at are very important. Here the example what we have taken, which having both real and distinct pole, and both the poles are located at the left hand side, so that's why we got the expression of e to the power at like this. So other examples also we will take where maybe multiple poles are located or the poles are located at the right hand side, then you will see how the elements of e to the power at are going to change. So from this discussion, one thing is clear, that what will be the elements of e to the power at and what will be the dimension of e to the power at. Means if the A is a square matrix n by n, then if you compute the e to the power at for that, definitely e to the power at also will be a n by n matrix, which is helpful to compute the solution of the system states, because you are finding that xt equal to phi t means e to the power at into x0. Fine. I will end my lecture. We will discuss how to compute e to the power at using Cayley-Hamilton theorem. I will show you only the result, but I will not show you here how this process has been derived from the Cayley-Hamilton theorem. So only I will show you the result, that how to compute matrix exponential. So the matrix exponential can be calculated e to the power at equal to k equal to 0 summation k equal to 0 to n minus 1 alpha k a to the power k. Okay, now if we want to calculate the e to the power, and n is the order of the system, so if a is n by n, so that's why it will go up to n minus 1. So now if you see the expression 7, if we want to compute e to the power at using this formula, we have to know what the alphas are. So alpha i's are determined, it will be from the set of equation given by the eigenvalues of a, where e to the power lambda it is equal to k equal to 0 to n minus 1 alpha k lambda I to the power k, where the lambda i's are the eigenvalues of a. So this how to use these two equations to compute the e to the power at, it will be clear if we will give if I will give an example, that will be clear. So I will give couple of example to understand this how to calculate the e to the power at using Cayley-Hamilton theorem. So now suppose one example has been taken. Find e to the power at for a 0 1 minus 2 minus 3 using Cayley-Hamilton theorem. So in your exam, if it is specified that you have to calculate the e to the power at using some specific process, you have to solve using that process only to be credited. Okay, so now so Cayley-Hamilton theorem is what it is telling. You see, it is telling that e to the power at will be equal to summation k equal to 0 to n minus 1. So n is here 2, so it will be n minus 1 will be equal to 1. Okay, so here you see expression n minus 1. So here it will be k equal to 0 to 1 alpha k a to the power k. So basically it is so k equal to 0, it will be alpha 0 plus alpha 0 into I plus alpha 1 a. So if we want to calculate e to the power at, we have to know alpha 0 and alpha 1. Okay, and if we know the alpha 0 and alpha 1, then if we substitute here, then we will get the expression of e to the power 80. And now the equation number 8 has given how to calculate alpha 0 and alpha 1. So that can be calculated if we know the eigenvalues of the matrix A, because it is e to the power lambda it. So let us calculate the eigenvalues of e to the power eigenvalues of the A matrix. So that's why we have computed the characteristics equation a square plus 3s minus plus 2, and the eigenvalues are minus 1 and minus 2. Okay, so now according to the formula, it is e to the power minus 1 into t will be equal to, means equation number 8 I am writing, okay, for the lambda 1, that is lambda 1 is equal to minus 1, that is k equal to 0 to n minus 1. So basically it will be, so here you see e to the power minus t will be alpha 0 minus of alpha 1, fine. And for alpha 2 equal to minus 2, you can write equation 8, that is alpha e to the power minus 2t is equal to alpha 0 minus 2 into alpha 1. So you will get the two simultaneous equation, and from here you can calculate what will be the alpha 0 and what will be the alpha 1. Once you will calculate the alpha 0 and alpha 1, then you substitute this in this equation to compute the e to the power 80. So this is the way you can compute the e to the power 80 using Cayley-Hamilton theorem. So now if you substitute in the main equation the values of alpha 0 and alpha 1, then you will get the e to the power 80 expression of e to the power 80. Fine. So here only the process I am showing, but I will request you to derive by yourself, then only you will get the feeling. And suppose another example I have taken, that will be the last example for this today's discussion, that is find e to the power 80 for a equal to 0 1 minus 1 minus 2. And most important thing here is that for this example we have the repeated eigenvalues, that is alpha 1 lambda 1 lambda 2 equal to minus 1, and it is a 2 by 2 matrix. So similarly e to the power 80 will be alpha 0 I plus alpha 1 a. And now the question is how to calculate alpha 0 and alpha 1, because here you are going to get the identical equation for the equation number 8, because here both the cases the eigenvalues are same. So for the equation 8 you will get the single equation. So if you have the single equation, then you cannot get the two unknowns, that is alpha 0 and alpha 1. So then I will tell you what is the process to avoid that things. So if you have the e to the power lambda t alpha 0 I plus alpha 1 lambda, where you are finding that you have the repetitive poles are there, then you will with the multiplicity 1, then what you will do, you will differentiate e to the power expression of e to the power lambda t once with respect to d lambda, and you will compute this derivative at the eigenvalue, that is minus 1. So if you do the derivative of d e to the power lambda t d lambda, you will get t into e to the power lambda t, and in this right hand side you will get only alpha 1, and you put lambda equal to minus 1, then you will get the expression of alpha 1 is equal to t into e to the power minus t. Okay, and now if you know that for lambda is equal to minus 1, you have e to the power minus t is equal to alpha 0 minus of alpha 1, and already you got the alpha 1. You substitute here, you will get the expression of alpha 0, and that is done in the next slide, that is alpha 0 is equal to 1 plus t into e to the power minus t. Then if you know the alpha 0 and if you know the alpha 1, you substitute the alpha 0 and alpha 1 in the expression of e to the power 80, that is a 2 by 2 matrix you will get. And most interesting thing is that if you have repetitive poles, then you will get in the form of t L minus 1 e to the power lambda t, and L is the L is the number of repeatable, L is the multiplicity of in the eigenvalue. So here multiplicity is 2, so that's why you will get the term like t e to the power minus t. Okay, so you can observe t into e to the power minus t, t into e to the power minus t terms are there. So this is the and here why I told you that that the elements, because these elements of e to the power at has to be observed for different cases when the pole locations are different, and then only you can try to understand that when we will discuss about the stability of the system, then the elements of e to the power at will play a key role to decide the stability of the system. Okay, so I will summarize what we have discussed in the today's lecture. First, we have started with a linear time invariant system, and then I told that we can solve it in two ways, that is using Laplace transform approach that we have discussed. Then I told that using time domain approach, and we have understood that if we want to utilize the time domain approach, then we have to compute the matrix exponential, which is known as state transition matrix, that is e to the power at. And then I have discussed one important case, that is solution of homogeneous equation where the u will be equal to 0, system will be driven by only the initial condition. And if we have that kind of system, then we have observed that to solve the system we also require to know e to the power at, means the matrix exponential. Then I claim that e to the power at can be calculated there are many ways are there, but we will discuss the three approaches, that is the Laplace transform approach, then the Cayley-Hamilton theorem, and diagonalization. But at this point I cannot discuss the diagonalization approach. We will discuss that one when we will discuss the topic that is similarity transformation. And then with the example we have understood that how to calculate e to the power at using Laplace transform approach and the Cayley-Hamilton theorem. And also we have importantly we have realized that what will be the elements of e to the power at depending on the eigenvalues of system matrix A. If the at least from the example we have seen that if we have a distinct pole, then e to the power at you can see that with the pole locations we or the sign of the poles, we can see that here they are present, that is -2 -1 are the pole locations for this, that is -1 -2. So here that's why it is e to the power minus t and e to the power means -1t and -2t terms are present, and also the dimension of e to the power at will be 2/2. And if we have a repetitive pole, then as I told you that the terms related to t to the power l minus 1 e to the power lambda t will be there, and l is the multiplicity in the eigenvalues. So I will stop here, and next class I will come with the properties of state transition matrix, and because these properties of state transition matrix also will help you to compute the e to the power at, and also we will discuss about the rest of the things, that is how to compute the solution of a non-homogeneous state equation. Thank you.